we're going to use the trapezoid rule to find the area under this curve. We're going to break it up into 5 sub-intervals, and we're going to use the trapezoid rule as opposed to in the past where we might have used LRAM or RRAM or MRAM. If we were to have used LRAM, we might have broken it up like this and used a bunch of rectangles. We can see that not that accurate. We're going to have lots of space that's not accounted for. With the trapezoid rule, you'll see that we will have a much more accurate estimation. There would be the first trapezoid, the second trapezoid would look like this, the third trapezoid would look like this, the fourth, and the fifth. And you can see it really closely is going to estimate the area under this curve. You can see right here this trapezoid is representing the very first one we have here, region 1. The width or the height of the trapezoid is delta x, which would be the width of each partition. Y sub 0 is the left side, y sub 1 the right side, but y sub 0 will be one of the bases, y sub 1 would be the other base, and we know the area of a trapezoid is half the height times the sum of the bases. So 1/2 delta x, y0 plus y1. And if we go to region 2, that would be 1/2 of delta x, y1 plus y2. This would be one base, y2 would be the second base. You go to y3, and y2 is the left base, y3 is the right base. You go to region 4, y3 is the left base, y4 is the right base, and you continue on. And we have all of the regions represented here, all 5 regions. Now, if we add up all those regions, 1, 2, 3, 4, 5, and take all of these and write them horizontally, you see we have region 1, region 2, region 3, region 4, and region 5. Each one of these has 1/2 delta x. We can factor that out. You're left with y0 plus y1, and then y1 plus y2 plus y2 plus y3 plus y3 plus y4 plus y4 plus y5. And you can see that there are 2 y1s, 2 y2s, 2 y3s, and 2 y4s. So all except for the first and last heights, you're going to have 2 of all the other heights. And so this is the trapezoid rule. You take 1/2 the delta x, which is the height of each trapezoid, and you take base 1 2 times the second base, and then of course they're sharing those bases, so it's going to be 2 times all of the heights on the inside plus each of the heights, the first and last height. The first and last are singles, and everything else is doubled, that coming from right up here after we factored out the 1/2 delta x. So the first example, we're going to use the trapezoid rule with 4 partitions to estimate the integral from 1 to 2 of x squared dx. So the integral from 1 to 2 has a distance of 2 minus 1. Dividing it into 4 pieces, each piece will be 1/4 of a unit. So delta x will be 1/4. That'll be the height of each of these trapezoids. And then you simply take each of the heights as going to be your bases of the trapezoid. And so what we'll do is we'll say it's half of the height, which is delta x, which is 1/4. And then it's going to be f of 1, 2 times f of 5/4, because this width is 1/4. So if this is 1 4/4, the next x value over will be 5/4. 2 times f of 6/4, 2 times f of 7/4, and then finally f of 8/4, which is f of 2. And so we have that listed here. This is our trapezoid rule. You simply do your calculations, plugging the numbers into the function x squared. So you got 5/4 squared is 25/16 times 2 is 50/16. 36/16 doubled is 72/16. 49/16 doubled is 98/16. and f of 1, of course, is 1, and f of 2 is going to be 4. You add all these up and multiply by 1/8, and you will get 75 30-seconds for the area under that curve, estimated with the trapezoid rule. 75 30-seconds is approximately 2.344. If you actually did the integral, it comes out 2.333, so a pretty darn close accurate estimation.